Welcome! Today, we're going to tackle a fascinating algebraic problem. By the end of this video, you will be able to solve the equation x squared plus y squared plus z squared equals xy plus yz plus zx. That's x squared plus y squared plus z squared equals xy plus yz plus zx. Our goal is to find all the possible real number solutions for x, y, and z. It might look a bit intimidating at first, but we'll break it down step by step. Let's see how to find the real number solutions to this seemingly complex equation. Let's begin by manipulating the equation to get it into a more useful form. We have x squared plus y squared plus z squared equals xy plus yz plus zx. The first thing we should do is move all the terms to one side of the equation. This is a classic algebraic move that can reveal hidden structure. So, we'll subtract xy, yz, and zx from both sides. Now we have x squared plus y squared plus z squared minus xy minus yz minus z, x equals 0. This equation is equivalent to our original, but it's now set up in a standard form that's often easier to work with. Our next goal is to transform the left side of this equation into a sum of squares. We're focusing on this expression, x squared plus y squared plus z squared minus xy minus yz minus zx. The reason we want to do this is powerful. The only way a sum of squared real numbers can equal 0 is if every single number being squared is itself 0. So, if we can show that our expression is a sum of squares, we can set each part equal to 0 and solve a much simpler system. This technique is a common and very useful strategy in algebra when you encounter equations that are quadratic in form, especially when they involve multiple variables like this. 1. Remember the key property. For any real numbers a, b, and c, if a squared plus b squared plus c squared equals 0, it must be true that a, b, and c are all 0. We're going to use this property to our advantage. Now for the clever part. Let's look at our expression again. We have x squared plus y squared plus z squared minus xy minus yz minus zx. To get a sum of squares, we can try to find terms that resemble parts of perfect square trinomials, like a minus b squared equals a squared minus 2ab plus b squared. Notice that we have dash xy, dash yz, and dash zx. These terms look a lot like the middle terms of squared binomials, but they are missing a factor of 2. For instance, x squared minus 2xy plus y squared is a perfect square. So, what if we multiplied our entire expression by 2? Let's see what happens. This is a common trick used to reveal hidden structure. Multiplying the equation x squared plus y squared plus z squared minus xy minus yz minus zx equals 0 by 2, we get 2x squared plus 2y squared plus 2z squared minus 2xy minus 2zx equals 0. This new equation, 2x squared plus 2y squared plus 2z squared minus 2xy minus 2yz minus 2zx equals 0, is equivalent to our original equation and holds the key to solving it. Now, let's rearrange and regroup the terms in our new equation. Remember, our goal is to find perfect square trinomials. The term 2xy in our expression, 2x squared plus 2y squared plus 2z squared minus 2xy minus 2yz minus 2zx, looks very familiar. It's the middle part of the expanded form of x minus y squared. Let's see if we can construct this. We have a negative 2xy term. We also have 2x squared and 2y squared. We can split those up into single x squared and y squared terms. So let's group x squared, y squared, and negative 2xy together. This gives us a perfect square, x minus y squared. So we'll write this grouping out. X squared minus 2xy plus y squared. This is exactly x minus y squared. We can do the same for the remaining terms. We have 2yz, which can be grouped with the remaining y squared and z squared terms. This forms the perfect square, y minus z squared. And finally, we have 2zx. We can group this with the last x squared and z squared terms. This gives us z minus x squared. Notice that we've used all of the 2x squared, 2y squared, and 2z squared terms by splitting them across these three perfect squares. For example, the 2x squared was used as 1x squared in xy2x and the other x squared in zx2x. Let's put it all together. We have successfully rewritten our equation. The original equation was x squared plus y squared plus z squared minus xy minus yz minus zx equals 0. After multiplying by 2 and regrouping, we now have x minus y squared plus y minus z squared plus z minus x squared equals 0. Now, let's reflect on this result. The left side of the equation is a sum of 3 squared terms. Remember our key property about sums of squares. Since x, y, and z are real numbers, the terms x minus y minus z, and z.x must also be real numbers. The square of any real number is always greater than or equal to 0. This means that x minus y squared is greater than or equal to 0, y minus z squared is greater than or equal to 0, and z minus x squared is greater than or equal to 0. The only way for the sum of 3 non-negative numbers to be equal to 0 is if every single number in the sum is 0. Therefore, it must be the case that x minus y squared equals 0, and y minus z squared equals 0, and z minus x squared equals 0. We've reached the final step of the problem. We now have a simple system of equations to solve for x, y, and z. Our system is x minus y squared equals 0, y minus z squared equals 0, and z minus x squared equals 0. Let's take the square root of each equation. From the first equation, taking the square root of both sides gives us the absolute value of x minus y equals 0, which means x minus y equals 0. Adding y to both sides, we find that x equals y. This tells us that any solution must have the same value for x and y. Let's do the same for the second and third equations. From the second equation, taking the square root gives us the absolute value of y minus z equals 0. This implies y minus z equals 0, so y equals z. This means that y and z must also be equal. From the third equation, taking the square root gives us the absolute value of z minus x equals 0. This implies z minus x equals 0, so z equals x. This confirms that z and x must be equal. We now have 3 conditions: x equals y equals z, and z equals x. Putting these together, the only real number solution for our original equation is when x, y, and z are all equal to each other. So, our solution is x equals y equals z. This means that if you pick any real number, say a, and set x, y, and z all to that number, it will be a solution to the original equation. Let's quickly verify our solution with an example to see that it works. We found that the solution is x equals y equals z. Let's pick a simple value, say x equals 1. Then, we must have y equals 1 and z equals 1. Let's substitute these values back into our original equation. On the left side, we have x squared plus y squared plus z squared, which becomes 1 squared plus 1 squared plus 1 squared. This simplifies to 1 plus 1 plus 1, which equals 3. On the right side, we have x, y plus yz plus zx. This becomes 1 times 1 plus 1 times 1 plus 1 times 1. This also simplifies to 1 plus 1 plus 1, which equals 3. Since the left side equals the right side, 3 equals 3, our solution, x equals y equals z, is correct. Any real number chosen for x will work, as long as y and z are the same. So, let's recap what we accomplished today. We successfully solved the equation x squared plus y squared plus z squared equals xy plus yz plus zx. We started by rearranging the terms to get 0 on one side. Then, we used a common algebraic trick. We multiplied the entire equation by 2, which allowed us to regroup the terms into a sum of 3 perfect squares. We used the fundamental property that the only way a sum of squared real numbers can be 0 is if each of those numbers is 0. This gave us a simple system of equations to solve. By taking the square roots, we found that x must equal y must equal z, and z must equal x. This led us to our final conclusion. The solution set for the original equation consists of all real numbers x, y, and z, such that x, y, and z are equal. You now know a powerful technique for solving equations that might not be immediately obvious. Great job!